I get a lot of people who are like, wait a minute, this is my only class on Friday. I won't be here. I understand that. But all of my classes are in the morning. So I have this one, I have one right after this, then I have lunch, and then I have another class. So all of my classes, I just said, no, I can afford the day. You guys get the day off. But now they're telling me it might snow, and that's going to fuck everything up. Well, no, because by the time they call off, I will be here already. This is what happens when I get up early to get here on to go to the gym before class. Um, is that I am here at 6 o'clock. So by the time they call off, I'm sorry, I have to be. I, I got told off by my doctor. I therefore have to be on my grind. But yes, that's why these aren't due until Monday. So, with that in mind, what questions do you have? Yes, ma'am.
But in section 2.5, question 32, there's a double, like an exponent. And I don't really know how to go about that. And there's also not another question like it, not section.
Oh, that e to the minus. Okay. So when I see this, I react with that's really thinking of the exponential function of minus t squared. So it's like there are parentheses here. So in order, I would take a number, I would square it, multiply by -1, and then take e to that result. So that's really three functions, one after the other. You square, you multiply by -1, and then you exponentiate. Yes.
So, it's for
4 for D, E, and F on 2, 6. So 2, 6, number 4 says, look at the picture and tell me what's going on. Okay. So let's look at the picture in number 3 on that same page. Here's my graph. This asks what's happening as I go to infinity. Well, that's this way, right? So I have a y value I seem to be approaching. I know what that is. I'm good. As I go to minus infinity, that's this half, and I'm going to a different one. So there's a different asymptote on this side than there is on this side. The horizontal line I would be going to here is at -2. Yes? The one over here is y equals 2. Well, that's already part of answering part E here. I know equations for these horizontal asymptotes. There are also vertical asymptotes here, because as I come in to 1, whether I come in from the left or I come in from the right, I'm going to positive infinity. So x equals 1 is also an asymptote here. And as I go to 3, I'm going to minus infinity, whether I come in from the left or the right. So x equals 3 is another asymptote. I think the same principles apply here for number 4. Because this is our picture, right? The difference is what's going on at 2 is not the same on both sides. So I'll need to look at the left and the right separately from one another. Make sense? All right. More questions. Doesn't. For 2 point, this is asking me to draw the curve now, right? So how about I do 7 since 6 is one of the assigned ones, right? Okay. So in 7, we are told the limit as x approaches 0 is infinity. The limit as x approaches 3 from the left is minus infinity. But the limit as x approaches 3 from the right is positive infinity. The limit as x approaches infinity is -1. And the limit as x approaches minus infinity is 1. I wrote those in the other order than they're printed in the book, but you with me so far? Okay. So that's all I know about this function. Here's my picture. I've got the axes all set up. I've put the places I know interesting things are happening on my axes because I'm told about x going to 0 and x going to 3. So I need to make sure I can see those spots. And then I'm told about a limit being 1 and -1 in the y direction. So that's why I have those on there. So the limit as x approaches 0 goes to positive infinity. That means it's got to do that from both sides because there's no sidedness on this limit. So both sides, as I get closer and closer to 0, need to be going up. So far, so good. I know as I get closer to 3 from the left side, I should be going down. As I get closer from the left side, I should be going down. As I get closer to 3 from the right side, I should be going up. So far, so good. This says that as I go to the right, more and more and more, my y values get closer to -1. Here is the horizontal line, -1. As I go further and further right, I should get closer to this line. This says that as I go further and further left, I should be getting closer to that line. Y equals +1, right? Now, I already drew this so it crossed that line. If I hadn't crossed the line already, I could just do the same thing and just approach it from on top. But since I've already gone past it, I'm going to have to keep going down and then come back up. I could wiggle back and forth. I could go over and under and over and under and over and under and have them get smaller as I go on. So it just continues getting closer to this y value.
So there's like multiple correct graphs to draw?
Oh, yes. And you'll notice I just connected the pieces in a way that I thought looked good. Yeah, you can do anything you want in the middle there. As long as you've drawn the correct pieces that you were told about, the rest of the graph is kind of play with it.
Thank you.
You're welcome. That's also why in the instructions it says sketch the graph of an example, not the example, because there are lots of options that would work here. More questions? Caden, Caden, can you, thank you. Ask me more things. Did I tell you guys the bad joke about asymptotes? Okay, so this kind of an asymptote is the one we most commonly think of, where you just never touch the line, right? Same thing here and here. With vertical asymptotes, you're not allowed to touch them. With a horizontal asymptote, you could, as we see here on the left, oscillate back and forth, as long as you're getting closer. So the joke I used to use is that when you're talking about vertical asymptotes, it's like being with your significant other in your parents' living room. You can get as close as you want, no touching. I know, it's a bad joke. Okay, I did tell you that. Good, good. It's important to remember that. Some of these jokes are older than all of us. I learned that one from somebody who had told it multiple times, older than me, so. The other interesting thing about an asymptote is it doesn't tell me how fast I'm approaching it, right? So I've drawn this as getting closer to that horizontal line fairly quickly. We're getting close to -1, but we've done it by the time we're out about 6 or 7, maybe 8, 9. We're pretty close. I could be really slow in getting, as long as that is the direction I eventually am going. Speed of closing in is measured by something else altogether. You know, you're still looking at it like it's bothering you immensely. Talk to me.
What direction to draw? That's confusing.
Okay, well, there are actually a number of different ways I could have drawn this, right? The only pieces I know are the ones explicitly said here. When I'm going closer to 0, I have to be going up. And really, that's just that bit right there. No matter what the rest of it looks like, when I close into 0, I'm going up. When I close into 3 from the left, I'm going down. But when I close in from the right, I'm going up. Same value if I approach from the left or the right. It's just, you're coming in, give me a direction. Which way are you coming in? If there's no symbol, I've got to be doing it from both sides. If there's a symbol, it'll either tell me left or right. And then I can draw the up or down appropriately. We did this with the values in the previous one, right? We had a limited, we approached it was like 3. So again, I'm going to hit this place coming from this side. How I get there, they didn't tell me anything. So I just need to know, I got to get here. What's the approach look like? It looks like a drunken bumblebee. And then the same thing is said here, only this time it says I'm going right. Or I'm going to the left. And it gives me a particular number to get to. So as I'm going right, I should be getting closer to -1 eventually. As I'm going to the left, I should be getting closer to 1 eventually. It's everything that's outside the circles is what I felt like making. But the circles are the things that are explicitly given to me in the instructions and the way this function looks. think of it like a police sketch. I was told they were this tall, all right, make a shape this tall. Heavy set, average, skinny. Okay, I have a rough, blue eyes, blonde, black hair, red hair. Give me a hair color. Oh, it was a blue hair. Okay, let me make blue hair. I can now start to fill in the things you tell me. The rest of it we'll figure out, but this is what you can tell me. Those are the pieces that I was explicitly told about. The rest of it I'm just filling in to make it look good. You're welcome. As odd as it sounds, I believe visualizations play a fundamental part in math, to the point where in some of my graduate courses, I had trouble understanding the material until I could draw even a bad picture to figure out what was going on. But as soon as I got a mediocre, it kind of looks like this, right? My instructor would go, kind of. And I'm like, okay, well, then what we're really trying to do is, and I manipulate the image and describe that. Yes, that's the right process. And then I can sit down and solve problems. When somebody walks up to me in that sort of a course and says, I want you to picture a left-handed spiral in a four-dimensional space with this metric, well, that's a graduate course question, but okay, it's a left-handed spiral. I can't draw it in 4 dimensions, but I can draw it in 3. So I know what a spiral looks like. It's left-handed, so it's curving this way. Okay. Now, what the hell does 4th dimension thing look like? All right, let me write some equations down. And now I can kind of follow that. Eventually, over the course of how many semesters you are in math or whatever your field of study is, the math you do will be visual and intuitive to you the more you do it. Even if that's nothing more than titration, dilution factors, volume comparative things with C1, V1 problems, or I'm doing joint rotations for biomechanics. The math you do will become your set of visuals. That's what this is eventually driving at. How does what's written on this page become a picture I can then use for whatever I'm dealing with? Thus endeth my rant on visual math.
You got the textbook?
Yeah, right here. What do you need?
Just.
There are 2 copies of the book in the Math Enrichment Center. Those are loose leaf copies and binders. You're welcome to use them as long as you stay in the library and the Math Center, ideally. I may even have another paperback copy in my office. I'll have to find it. More questions? Yes.
I don't know where it's at, or the problem we did, talked about first that y equals x squared minus 2 over 3x squared plus 7, you know, similar to that.
Oh, so let me make something up like that.
Yeah.
Are we going to go to infinity or negative infinity?
Okay.
So I'm winging it. 2x squared minus 5x plus 3 over 7. We'll do x squared again, plus 4x plus 1. Okay. There's the shortcut version and then there's the long version. What's the shortcut version?
Find by the pull it out so that Like, I know the other one, the shortcut was like multiplying by 1, but it was like x squared over x.
Technically, that's the long one, not the shortcut, but yes, that works. That's the long version. I would say, oh, my highest power is x squared. So I'm going to multiply by 1 over x squared and 1 over x squared, right? That's absolutely correct. And that is the correct way to do this. Because then I say, okay, 1 over x squared times 2x squared is 2. 5x over x squared, x over x squared is going to cancel. I'm going to get minus 5 over x. And then I'll get 3 over x squared, right? And on the bottom, I'll have a 7 and 4 over x and 1 over x squared. That's absolutely correct. But now I take the limit of all of these pieces separate from one another. I take the limit of the top versus the limit of the bottom. And I say, well, I'm adding and subtracting so I can do each one on its own. So I say, as x gets bigger and bigger and bigger, what happens to over x squared? So that's going to go to 0. Same thing with this, right? Same thing with this. So really, all 4 of those pieces are going to go to 0. And that makes this limit 2/7. The shortcut. If the powers are tied, just look at the numbers. It's only in the cases where the powers aren't tied that I go through this walkthrough. Or if I want to justify it, it says, show your reasoning. This is what I'm going to do. Now, since this is a rational function, polynomial on top, polynomial on bottom, I will get the same limit when I go to minus infinity as I do when I go to positive infinity, because a rational function has at most one horizontal asymptote. We went to minus infinity, so we did the one on the left. If I did the one on the right, I get the exact same thing. Better? More questions? I think I wrote something about the powers being on top being bigger, on bottom being bigger in class the other day. If the power on the bottom is bigger, it's going to be 0. And if the power on top is bigger, it's not going to be a horizontal asymptote. So this equation does not have a horizontal asymptote. Because the power on top is bigger, there's no horizontal asymptote. I could still ask, what's going to happen as x goes to infinity? Or what's going to happen as we go to minus infinity? I could still want to know what's going to happen. But the fact that I don't have an asymptote means this is, as x gets bigger and bigger and bigger, this is either going to go bigger and bigger, or it's going to go negative. It just can't stop, right? So one of the questions is, how can I tell? Are we going up or are we going down? And is it the same on both sides? There are a lot of kind of hand wavy ideas I can do here. But if I really want to do it right, I should divide. Because isn't that what a fraction is? A fraction is division. A long time ago in an algebra class far, far away, I learned how to do division. Did you ever see something like this? Polynomial long division? If I do this division, I will get a quotient and a remainder. Let's actually do it. I say to myself, I want to divide an x cubed by an x. Well, x cubed over x is x squared. So I'll put that here. I multiply this by this. And then I subtract. Just like I was dividing numbers. And I did division by hand a long time ago. Okay, x cubed minus x cubed, that's gone. Nothing minus a minus becomes plus 5x squared. Bring down the next piece and repeat the process. 5x squared divided by x is 5x. Multiply. And subtract. 2 plus 25 is 27x. 5x squared minus 5x squared, they cancel. I bring down the 1. 27x divided by x is 27. Multiply. 27 times 5 is 135. Subtract. Those cancel. 1 plus gives me 136. Remainder, quotient, right? That means that this is equal to with a remainder of 136, right? So I'll write the remainder as a fraction. If I divided by 3 and had a remainder of 1, I'd have a 1/3, wouldn't I? So I have a fraction. If I want to take the limit as this goes to infinity, I can take the limit as this goes to infinity. And then I can say, well, the limit as x goes to infinity of this stuff as x goes to infinity, what happens to this piece? It's 0. This is going to stay 27, isn't it? This is going to be really big, but this is going to be even freaking bigger. So we're going to go to positive infinity because this is really going to behave like a parabola, which means if I were to really draw this picture, I wouldn't see a straight line for an asymptote. I'd see a parabola for an asymptote. That's weird. So we don't actually call them asymptotes when they're not straight lines. And this, huge, positive. This is 0. So that means this is going to end up going to infinity. The biggest power is the only power that matters, and it's going up. By the way, if I'm going to minus infinity, I'm squaring. It's still going to be positive, isn't it? Yes, both limits go up. This long division idea we'll come back to because it's really helpful for at least 2 other things later in the semester. There are 2 really good videos on polynomial long division on, of all places, Khan Academy. And there should be a link to that in our Canvas page. Please take a look. More questions? And by the way, this is why, in spite of having calculators, we still teach people to divide stuff by hand. Yes,
So, sketching a discontinuity in a graph, you would just like have like a dot or like a space in your contract, right?
Depends on what kind of discontinuity, right? Because there are several kinds of discontinuities. There's a discontinuity that's just a hole. Yes? So I could have a line with a hole in it. That would be discontinuous. I could also have a jump. That's another discontinuity. I could have an asymptote. That's a different kind of discontinuity. So there are lots of different kinds of discontinuities. I could have a graph that did this. I could have a graph that did this. Right? There's an asymptote there. It's not continuous. I could have a graph that did this. There's a jump. They're all not continuous, but they're not continuous in different ways. So the question that I know you're asking about roundabout, when I wanted to do the intermediate value theorem, I want you to draw me two different graphs. One of them that hits the value, the other one that misses. Take a look at those three pictures. Which one would be the easiest to make miss a value on the y-axis? Yeah, because there's that big jump in the middle, right? Which one would be easiest to make a value? Or the other one, right? Because it covers all of the y values, doesn't it? And so does that, except that one y value. So maybe I could make that hit the value I want.
but yes, again, this is another place where there are lots of possible pictures that work.
One of the reasons I threw that problem at everybody is to make you think about what it means to be discontinuous and to show that the continuous part of the intermediate value theorem is what makes it work. When my function is continuous, I am forced to hit all the values in between. But if I allow it to not be continuous, sometimes it works and sometimes it doesn't. It's the if-then problem. If I'm continuous, I must hit all the values. But if I'm not continuous, well, then I don't care what you say about the values. Sometimes you can hit them and sometimes you can miss them. You didn't satisfy the terms of the contract.
That's a discussion for formal logic, discrete math. I was at a talk this past summer by Marshall Ransom out of Georgia. And Marshall was talking about the intermediate value theorem and about several of its corollaries. There's another couple of value theorems we'll do later in the semester. There's the mean value theorem. There are two versions of that. There's the extreme value theorem. But they all start with assumptions about our function. Our function is continuous. Our function has these other properties. Then this is what we know. And he said, is it possible that you could look at the hypothesis differently? What if we lose this condition and replace it with something a little weaker? And he goes through this presentation about 20 minutes, and he says, some of you may know this. This is Darboux's theorem. I'd never heard of Darboux in this context. And the guy behind me starts to laugh because the guy behind me, his PhD thesis was on Darboux. He's like, I know all about this. I'm like, I don't know any of this. So I took a copious bunch of notes, but I realized it's just beyond how deep I want to get into the mechanics in this course. It's a great discussion for the theory of calculus course that none of you are going to take. Unless you're a math major, nobody takes the theory of calculus course. But it's why does this work this way, and can I tweak it? What happens if I change this idea just a little? Darboux is a smart guy. By the way, just because he's French Darbo is Darbous. So if you're interested in learning something weird related to the intermediate value theorem, look up Darbo. Or come talk to me, I'll give you Marshall's notes, because I took a lot of them. More questions, ask me more things. Oh, wait, I can't say every word. I brought twice. Get back on that. Come on, people, ask me questions. Keep me out of trouble. I will again say, I am a rank amateur. I know people who make a living like this. I spent my living doing calculus, so. This is just dumb time. The consolation of Ryan. I don't have a reason to keep you nailed to these chairs. This is question and answer. This is your time. What do you want to ask me about this assignment or about the course in general? This is the place to do it. Otherwise, I got no reason to keep y'all for it.
Wait, when's our first exam?
Officially at this point, I believe it's the 20th. No, it's the 18th. So we are here. The exam is 13 days from now. I believe if you look on the Canvas page, the first review sheet is posted. We just have 4 more sections to get through, right? No, 3 more sections. 1, 2, 3. And then we do the review next Friday. Oh, yes. The review sheet is way longer than the exam.
Thank you.
You're welcome. Correct. One, 2, 3, 4. You're very welcome. Back, thank you.